Hello, today we'll have oxidation reactions. So oxidation reactions can take place by metal oxidants. So today let's see the oxidation reactions with manganese 7 and chromium 6 oxidants. Manganese and chromium 6 oxidants are mostly have manganese 7 and chromium 6 oxidation states. So I'm just writing here manganese and chromium oxidants have generally, or we can say more often, generally, or more very often, or you can say very often, they have manganese 7 and manganese 7 and chromium 6 oxidation states respectively. Okay, so here we are using for the oxidation of reactions with manganese and oxidants. They have manganese 7 and manganese chromium 6 oxidation states. They tend to lose. So when the reaction takes place, they tend to lose, or they tend to accept one electron, so one odd number of electrons during organic reactions, organic oxidations. So in the oxidation reactions, they tend to accept odd number of electrons. Okay, so now let's see manganese oxidation. Generally, what are the compounds generally used? In the case of manganese, we use generally manganese oxidants are manganese 7 oxidants are generally most commonly what we use is potassium permanganate, KMnO4, potassium permanganate, which can be used either in acidic medium, or in neutral, or in basic conditions, in basic medium. Okay. Another is about manganese oxidation, and for chromium 6 oxidants, so many are here. They are also very strong, good oxidizing agents. They are chromium trioxide and chromic acid is CrO4, and present sodium dichromate or potassium dichromate, Cr2O7, sodium or potassium dichromate, and chromyl chloride or CrO2, Cl2, chromyl chloride, and then this PCC. PCC means pyridinium. We'll take later on. Okay. Pyridinium chlorochromate. Okay, these are all oxidizing agents used for oxidation of organic substrates using these reagents. Okay, generally they take place by accepting the electrons from them. So this is about let's take up about these two compounds. In the case of manganese, there is gain of 5 electrons takes place. I'll write down here oxidation reactions. So manganese 7 compounds gain accepts 5 electrons or gain 5 electrons, while chromium 6 compounds gain 3 electrons during oxidation. So here oxidation reactions, manganese 7 compounds, manganese potassium permanganate compounds, you say potassium permanganate gain 5 electrons, while chromium 6 compounds like chromium trioxide, potassium dichromate, so they gained 3 electrons during oxidation reactions. So oxidation reaction of organic compounds, so I write on here manganese 7, so on it accepts 5 electrons to give this manganese 2, so it is to minus 2, and which is they are all in acidic solution, and whereas so here the color it changes takes place. So transfer here purple color of manganese 7 permanganate. So after oxidation it will come to pink color. Change the color to from purple to pink. Similarly, chromium 6 compounds. So here 3 electrons are involved here. So 3 electrons have also here changes to chromium 3. Okay. Now this is also in acidic solution. Okay. So here the color also like this, from here orange color to changes the orange or red color, potassium dichromate or chromium trioxide. Those are changes to green color. Okay. So by changing the color, you can say that reaction is finished or not, like that. So today let's take up first one, that oxidation reaction with potassium permanganate. Okay, first let us take up reaction with potassium potassium permanganate. So today let's take up potassium permanganate. Oxidation reaction with, you can select KMnO4 here, KMnO4, potassium permanganate. So let's take up first one. Potassium permanganate is a good oxidizing agent, but the reactivity of the potassium permanganate depends on the solution we use in the media what we use. Okay, so here I'll tell you that that's what I write down here. The reactivity of potassium permanganate. So reactivity of KMnO4. Depends on the what is medium or what is a medium or solution. Depends on the medium or solution or it. So medium, okay, media, you can say. So whether it is used on acid or neutral medium. So it depends on the medium use. That is maybe whether it is used in acid or alkali or in neutral medium. Okay, neutral medium. So depends on the nature of this neutral acid, alkali or acidic alkali or neutral conditions. So depending on the conditions, so the reactivity of KMnO4 also changes. Okay. So here in acid solution. So here it is reduced to the KMnO4 reduced to the tribenzene oxidation. That is 5 electron net transfer of 5 electron takes place in acid solution. 5 net electrons transfer takes place. That is net 5 net electron transfer takes place. That is KMnO4. Potassium permanganate, or you say Mn7 is reduced to Mn2 plus. Okay, manganese 2 plus reduced to Mn2 ions. You can say manganese 2 ions. So with the net transfer of 5 electrons. So in the acid medium we have Mn 7 to 7. So here transfer comes to Mn 2 plus with net transfer of 5 electrons. So here 7 to 2 electrons, manganese 2 status takes place. So for example, I am giving here for a oxidation, the oxidation of secondary alcohols by potassium permanganate. So here MnO4, so manganate here, potassium permanganate, and reduction of this secondary alcohol. So in presence of acids, it's a solution. So it turns to these two, this alcohol, secondary alcohols are reduced, oxidized to carbonic compounds, like carbonic ketones. So secondary alcohols are oxidized to ketones. So the reaction is here manganese 2 plus water. Okay. So you can balance. So here I am repeating again. By using potassium permanganate, so oxidation of secondary alcohols to ketones takes place in the acid medium. So here we can balance the equations. So here 2, 5, 6 H for acid medium. So this will be 5 is 5, and here 2 manganese 2 plus, and iodine 2. So it is balanced like this. So in acid mediums, so we use 5 from here manganese 7 here, manganese 7. So 7 plus, you can write 7 plus 2, 7 plus is this 2 plus. Okay. So here this is in acid solution. So now next I will talk about in neutral or acid in basic conditions. Here net transfer of 3 electron takes place. Okay. And so here. So in the case of neutral, so while in neutral or alkaline or basic conditions, net transfer of 3 electrons takes place. 3 electrons takes place. 3 electrons takes place. So here there is the more generally potassium permanganate in basic or neutral conditions. Usually manganese dioxide there is generally manganese dioxide. So 4 is manganese dioxide is usually formed. Manganese dioxide is Mn4, okay, is generally formed. Then is from Mn7 to potassium permanganate to manganese dioxide, it is Mn7 to Mn6 4 takes place. As I write down here, Mn7 potassium permanganate to Mn4 takes place. So here the transfer of 3 electron takes place. So in reaction to similarly earlier cases, we can write the reactions of these oxidation of secondary alcohols to ketones in presence of potassium permanganate in basic solution or acidic in alkali solution. So here MnO4 in presence of oxidation of this secondary alcohol to these ketones, carbonic compounds, so manganese dioxide is formed. So here from -7 to here 7, so it comes to 4 like this. Then we have water, then plus OH, okay, plus OH. So that means here in the presence of in alkali medium here or in neutral mediums, secondary alcohols are oxidized to ketones in presence of MnO4. So we can balance this also like this. 2 here, 3 are used, 3 electrons are transferred. So 2 MnO2, manganese dioxide, 2H2O, and this 2OH. It's okay. So here for I have sent that manganese 7 is reduced to to manganese 4 like this. So here 3 electron transfer takes place. So it is in about in neutral or basic conditions, alkali conditions. So now let's take up one by one how oxidation of oxidation of this double bond, oxidation of this aldehydes to acids, and oxidation of this alcohol, secondary alcohols to ketones. So let's take up first again oxidation of secondary alcohols to ketones by using this KMnO4. Okay, I'll write down here oxidation of secondary alcohols to ketones. Oxidation of secondary alcohols to ketones by potassium permanganate. So you can here also you can discuss in the acidic medium so how ketones are alcohols are oxidized to ketones. So here aqueous solution of potassium permanganate may be used to oxidize the secondary alcohols to ketone. So here I will give one example. Okay, for example here CH3, secondary alcohols. So another one. So any is a substituent here. So using acid conditions, KMnO4, potassium permanganate in magnesium sulfate in acid solution, in aqueous solution, in presence of sodium hydrophosphate, CO4, okay, sodium hydrophosphate. So in acid medium, this is oxidized to this alcohol, secondary alcohol is oxidized to ketones. So we have CO2, ET. Okay. So one example I'm giving, many examples are here. So I'm giving one example. So let's see the mechanism of the reactions. Mechanism of the oxidation of secondary alcohols by KMnO4. So let's say generally, I'll write down here. Okay. Oxidation of secondary alcohols to ketones by KMnO4 in acid medium. So I'm writing here mechanism of the reactions. So first, let's say general mechanism here. This is a secondary alcohol. Okay. So secondary alcohols first in the presence of acid medium. So this one always is protonated. Okay. Protonated. So in presence of acid, so it becomes OH2 positive charge here, now prime here. So now secondary alcohol is protonated in presence of acid. Then loss of this water, so this will give RCH, R prime, okay, positive charge plus water, loss of this one. So this one reacted with potassium permanganate. So you can write here also no, KMnO4 or MnO3 is negative charge, and yeah, I can write down here negative MnO3 K plus. The structure is like this: MnO, okay, this is okay, here it's charge here like this. So this is potassium permanganate. So this negative charge attack here. So but first step is formation of this. So this is MO negative MnO3 K plus. So we can write this way. This KMnO4. So take here. So first step is formation of this intermediate or MnO3 like this. Okay. So it is first step is this form. So you can write. So here, so hydrogen here. Okay. So in the presence of water, hydrolysis in water, like earlier one water is there, so loss is there. So attack here again from this one, so loss this one. So finally you got this ketone, oxidized to ketone, and then in this one is product 2 got is MnO3 negative charge. Okay. So this MnO3 can be again hydrolysis. You can have you can use the KMnO4 again 3MnO3. So this is hydrolyzed water. So you get MnO2, 2 here, plus MnO4, plus some permanganate, plus 2 OH. Okay, this way you can use this one. So this compound, this anion, manganese trioxide anion can be reused by hydrolysis. We got this potassium permanganate. So this is the mechanism for oxidation of secondary alcohols to ketones. So I'm repeating again. So first we have secondary alcohols here. This secondary alcohols in presence of acid is protonated and loss of water molecules. So we got this carbocation, then attacked by this permanganate. So we got this intermediate, then water attack here, pick up the proton, loss of the proton, rest of the proton. So we got a product, ketone, and this one. This manganese trioxide anion can be get plus permanganate again by reacting water hydrolyzed with water. So it is about the oxidation of secondary alcohols to ketones. So next I got oxidation of aldehydes to carboxylic acids. Okay, so next reaction is oxidation of aldehydes to carboxylic acids. So now oxidation of aldehydes to carboxylic acids by KMNO4, by using the KMNO4. Okay, so here now so many examples are here. So in the aqueous solution of KMNO4, here it is aqueous solution of KMNO4 under either acidic or basic conditions can be oxidized to carboxylic acids. So for example, I will write them here. C6H13 cyclohexyl, H13, C6H13 CSO. This is aldehydes in presence of KMNO4. So in presence of sulfuric acid, in acidic conditions, sulfuric acid, so in aqueous solution at room temperature, like 25 degrees Celsius, so it will be oxidized to acid. Okay, C6H13, CO2H. Okay, so aldehydes are oxidized to like this. So you can another examples I can give. Another examples say like this. So we can have O here, this is protected one. Okay, so it is aldehydes. Then you get same reactions KMNO4 in water medium. So it can be neutral conditions around 70 degrees Celsius to 72 refers, or in water means conditions in boiling water conditions. So here this is oxidized, the aldehydes are oxidized to carboxylic acids, CO2H. Okay, same case, this is protected. Okay, it's protected like this. So what I want to say that aldehydes can be oxidized to carboxylic acid by KMNO4 either in acid solution or neutral solution or in basic conditions. So let's see the mechanism of oxidation of aldehydes by KMNO4. So let's see the mechanism now. Okay. Oxidation mechanism. Okay. Mechanism of the reactions. Oxidation of aldehydes by potassium permanganate in acid solution. In acid medium, let's first take acid medium. So let's have one example here. So RCO is, okay, this is aldehyde. So first in the presence of acid medium, so we get this one RC protected. This will be protonated. The first will be protonated. So we got this OH positive charge, this aldehyde. So it can be written as like this RC, so like this. So we can have OH here and this positive charge here. So this This way we can write. So now this can react with this potassium permanganate like earlier cases. So we have MnO3 negative charge positive potassium permanganate. So this attack here. So we got first we got this COOH, COOH is okay, then OMnO3. This OMnO3 we got this one. Okay. So now we got this one. Then like other cases, water attack here. Like water attack other cases. Water attack here, water pick up the proton. So here come like this, so it lost like this. So we got a acid RCOH okay plus MnO3 negative charge. Trimethyl manganese trioxide and then okay, this first we got this one. This again like earlier cases, this can be coming back reacted with water, MnO3 with water. So we got this MnO2 earlier cases like MnO4 and then 2 OH, okay, OH. So we can thus yeah. So we can show here two are here used, 2 MnO2 is here and then 2 OH, okay. Earlier some other one. So I'm repeating again in the mechanism of oxidation of aldehydes to carboxylic acid. In here we use the acid medium. So first aldehydes are protonated and then you got this carbocation, they react by permanganate. So you got this and attacked by water here. So lots of this proton. Then we got here compound acids and then Mn trioxide radical, which can be hydrolyzed to give this permanganate. So it can be reused again this one. So this is about the oxidation of aldehydes to carboxylic acids. Now lastly we have let's come to oxidation of carbon-carbon double bonds by using this KMnO4. So oxidation of carbon-carbon double bonds by KMnO4. Okay. So here also reaction can take place either in acid medium or neutral medium or like this. Okay. So in the case of alkali or neutral mediums, so double bonds are reduced to 1,2 diols, and in case of acidic mediums, so they are reduced to this alpha ketones. I write down already. Okay. So so this oxidation depends on the nature of the oxidation of carbon-carbon double bonds depends on the medium, on the conditions, on the reaction conditions. Okay, so either in acid, in acidic, or neutral, or you can say basic conditions or alkali conditions. So here we can discuss this two ways. So first, in the case of acidic mediums, so double bonds are reduced to, so I write on here C. So you can write two ways. Okay, first one is acid. In acid medium KMnO4, acidic conditions KMnO4. Here also is basic condition, acidic condition. In basic condition KMnO4. We can have two types of products. We can have here. You can have these ketones, alpha. Okay, let's say hydrogen here, one hydrogen here. Okay. So here you can have hydrogen here. So let's see one hydrogen here. Okay. So you can have CH here. So we can have CH here, one hydrogen here. So hydrogen here like this. So another here. So we can have like this. You got this product like this. So so you use this to one hydrogen here like this. Okay, this type of so addition oxidation takes place like this. Okay, this kind of double bond. So first in acidic medium, so we got a alpha ketol. See, here we got is ketol, alpha hydroxy ketone. You can say alpha ketol. Always here, okay. So you can set alpha in the alpha position, alpha hydroxy ketol, or you can say ketol alpha ketol. Simply you can say ketol. So alpha hydroxy ketol or alpha hydroxy ketone, or you can say alpha ketol. But in the case of the basic conditions, so you can be in two. You have CH 1,2 diols, CH say 1,2 diol. You can say 1,2 diols. So repeating again. So oxidation of carbon-carbon double bonds by potassium permanganate can take place in two conditions. First will be in acid conditions, one will be in basic conditions or in neutral conditions. So in the case of acidic conditions, so formation of alpha ketones takes place. So alpha hydroxy ketone. So here acidic conditions, and in the case of basic conditions or neutral conditions, it takes place this formation of 1,2 diols. Sometimes, okay, in some cases, in broken down, this also takes place. Cleavage of this double bond takes place in the acid conditions. In acid conditions, sometimes broken down to this takes place. So I'll give example of this condition. Okay, oxidation of carbon-carbon double bonds by potassium permanganate. So mechanism or some examples, I'll give some example here. Some example, say C1C ice. Okay, this is CH2 7 acid here, and here also CH2 7 CH3. So there are cis cases are. So you can have two types of reactions we'll have. So here we can use KMnO4 in alkali medium, so hydroxide aqueous solution. So first formation of this 1,2 diol takes place. COOH, and this the hydrogen here. That's the hydrogen here, hydrogen, and this one is the substituent CH2 CO2H. Here also CH2 CH3. Okay, so here I got 1,2 diols CH product, and we use so we are using alkali medium. So now we use in acid medium KMnO4 aqueous solution water. In acid medium magnesium sulfate or sulfuric acid, and sulfate. Then we got this hydroxy ketones, alpha hydroxy ketones. So let's write CH3, substituent CH3, CH2 and CHOH, yes, COO, then this substituent, okay, CH2 CO2H. Okay, so you got alpha position, alpha hydroxy ketone, or you can say alpha ketone. So it is an example. So it is an example of the oxidation of carbon-carbon double bonds in two mediums. So let's see another examples how the bond broken take place in the. So I'll show you a cyclic compound, a cyclic ketone, so cyclic double bond. Okay, to give these two types. So let's say this compound. Okay, let's say this one. So let's see when you use this two types. So pass is KMnO4 in alkali medium, so hydroxide in aqueous solution. So first this will be oxidized to 1,2 diols. So we'll get here, no problem. We got this in there. This ice here, then this ice here like that. Okay, so we got this product 1,2 diol. But in the case of use KMnO4, you use KMnO4 aqueous solution in the presence of sulfuric acid or magnesium sulfate in acid medium. The acid medium, then we got another product. Okay, so we got here broken of this takes place. So here, this one is broken down here. So in acid medium broken down of this to keep this aldehyde groups are occur. So let's see how the mechanism of the formation of these products. So let us see the formation of this mechanism of these reactions. So mechanism of oxidation of carbon-carbon double bonds by KMnO4. So mechanism here, mechanism of the reactions, oxidation reactions. So let's say general reaction here, CHR, so CR prime, CS, okay. So now MnO4, so we have like this, potassium permanganate, okay, this is K here, okay. So cyclic intermediate takes place. So you take here first, then attack, then like this, okay. So here and then attack here, carbon, then double bond goes to the oxygen like this. So we got a cyclic manganese ether got manganese ether is obtained. So here a cyclic intermediate is obtained. So here R is C R prime is, so you have O, Mn, double bond O negative charge here. So you got a cyclic intermediate. So you're going to see cyclic manganese ether. You can say manganese ether. So this one obtained. So when you hydrolyze this with water attacks here. So we attack this. First will be like this. So you got this one. So RCH. So write down here RCH. O negative means pick up the water. So it becomes OH. Then CRCH. O MnO3. You can say here MnO2. Okay, so here 2 are here MnO2. So purpose is this one, okay. So further reacted with alkali OH here alkali solution. This will give this 1,2 thiols in alkali solution. Okay, R prime here. So 1,2 thiols obtained in presence of alkali. So then use this further. Another KMnO4 or manganese dioxide and manganese permanganate. So it can be converted to MnO3 or CH, OH, C. So you can write CHO MnO3 converted to this MnO2 converted to MnO3 or prime like this. Okay, so this is converted to R, CH, OH, then you can write this way R prime here. Can you see? Okay, I write it here. You can see here. This one you can see. So first we got this one R, CH, OH, then CH, OMnO3 converted to MnO2 converted to MnO3 R prime. So this is again react to, so part we will keep this water. So we will give R, CHOH, then C double O R prime. So this is alpha ketol. So this is the reaction mechanism. Or if you use, this can be broken down this way. First will be, this will be like this, and this will be like this, okay. No, this way. So like this we can have, this one will be broken down also, this way. So here you can have two molecules of aldehyde, RCHO plus R prime CHO. So broken down this, or then you got the MnO3 negative charge, which can be hydrolyzed together like aldehyde gases. So we got RCHO and R, RCHO and R. So you can see this one, okay. RCHO plus R prime CHO MnO3, okay. So this way, so broken down take place. So double bond is broken down. So we can have, so I'm repeating again. So first this carbon-carbon double bond reacts with this permanganate. So we got a cyclic manganese, manganese ether, so which is in presence of water. We got this intermediate in presence of alkali basic conditions. So attack here. So this attack, so we go OMnO3. So here we got this alpha 1,2 diol. Okay, so it is in the conditions of basic conditions or in alkali, so 1,2 diols. But in presence of acid medium, so first is converted to MnO2 is converted to OMnO3, then so in loss of this we got alpha ketone, or can broken down this way, so to give this one aldehyde groups, another aldehyde groups, and OMnO3. So this is the mechanism of oxidation of carbon-carbon double bonds. So I'm repeating again now. So I'm summarizing for today's lectures. So we have discussed about the oxidation of using this potassium, potassium permanganate and chromium dioxide. Oxidation reactions with manganese 7 and chromium 6 oxidants. So mostly manganese and chromium 6 are used for oxidations are generally manganese 7 and chromium 6 oxidation states. So in the case of manganese oxidants, we have generally potassium permanganate, and for chromium 6 oxidants we have chromium trioxide, chromic acid, potassium dichromate, sodium dichromate, chromium chloride, or PCC like this. So in the case of manganese 7 compounds, so gain of 5 electron takes place, but in the case of chromium 6 compounds, gain of 3 electron takes place. So first we'll discuss about the oxidation with potassium permanganate. So in the case of potassium permanganate, the reactivity of permanganate takes place depends on whether it is used in acid medium or neutral medium or basic conditions. So depending on the conditions of the mediums, so you can have different types of reactions. So in acid solution, the potassium permanganate is reduced to divalent manganese ion. So there is transfer of 5 electron transfer takes place from manganese 7 to manganese 2 takes place. Similarly, in neutral or basic conditions, 3 electron transfer takes place, that is from manganese 7 to manganese 4 takes place. So here generally manganese dioxides are formed. So we can discuss first oxidation of secondary alcohols to ketones, that we have already discussed. Then second is oxidation of aldehydes to carboxylic acid, and third one is oxidation of carbon-carbon double bonds. So we have different conditions. We have in acid medium, so we have got different products, and in alkali medium we got different products. So this is about today. So next class we will have oxidation with chromium 6 oxidants. So this, okay, I will wind up here today. Okay.